Okay, good afternoon, everyone. We're going to start with the afternoon session. So it's my pleasure to introduce Constantinos Daskalakis, who's a professor at MIT in the EECS department. And he's also an investigator in the Foundations of Data Science Institute. He works on the theory of computation, its interface with game theory, economics, probability theory, machine learning, and statistics. He studied equilibrium, mechanism design, and the interface of property testing in high-dimensional statistics. He's won a large number of awards, starting from the ACM Doctoral Dissertation Award for his PhD thesis, but recently also the Simons Investigator Award, the Nevin Lena Prize, which has been renamed the Abacus Medal, and many, many other awards. And I guess without further ado, I'll pass it on to Kostas. Thank you.
All right. Hi, everybody. Thank you very much for the great honor to speak at the 10th anniversary of the Simons Institute. It's no better place to celebrate the achievements of theoretical computer science over the past 10 years, but also, also the foundations that were laid before those 10 years for these developments to take place. This talk is about some interesting points of contact between theory of computation, optimization, machine learning, and game theory. And it's about multi-agent learning. So as you all know, machine learning over the past 10 years have made important breakthroughs. And these breakthroughs are already being used in real life. So from image and speech recognition to translation, these are definitely in the real world. And a lot of recent developments in text generation and protein folding are bound to have a lot of impact in our world. So from an optimization standpoint, for the most part, a lot of how these breakthroughs are attained is to write a learning problem as an optimization problem that typically involves a very high-dimensional variable, a loss function that is typically non-convex, but which at least is Lipschitz and smooth, at least almost everywhere. And to try to solve this problem, which is very hard because the function is non-convex, with a very simple method, namely gradient descent or some variant of gradient descent. Now, because the function is non-convex, there's no guarantee gradient descent is going to get to global optimum, which is sort of like the fixation of, for a large part of theory of computation. But nevertheless, we have a guarantee that gradient descent will get to a local optimum. And the empirical finding is that these local optima are pretty good in many applications. So now, this empirical finding is so common that this has led to a very common paradigm in this space, which is for a learning application that you're interested in, write a very complex model, like a large neural network of some architecture, collect a lot of training data, write down a loss function that expresses how well your model does on the training data, get access to a supercomputer and try to minimize your loss function using the simple procedure I was talking about before. And this is a framework, okay? So again, we have no guarantee that we're going to get global optima, but at least we know we're going to get to local optima. And there's an optimization framework that allows us to write models and train them using gradient descent. The success is so large that there's a debate going on, right? So a lot of people are very gung-ho about this paradigm actually working modulo the size of the models that you can write and train. Again, this debate of scale is all you need is a recurrent debate, a recurrent opinion in this field, which of course has a lot of people agreeing and a lot of people disagreeing with it. Now, that's not single agent learning is not the topic of this talk. I want to talk about a A type of learning where this scale is all you need is not an opinion that is supported a lot, because it's pretty clear that scale is not all you need. Definitely is not all you need. And this is the context of multi-agent learning. So a lot of emerging applications in machine learning involve settings that are either explicitly multi-agent, like playing complex games and multi-robot interactions, or self-driving cars interacting with other self-driving cars on the road, or with humans on the road, or which are implicitly multi-agent. These are like deep generative models and training classifiers that are robust against adversarial attacks. These are applications that are not born as multi-agent learning problems, but there a multi-agent learning formulation helps you attain a learning goal that is otherwise a single agent learning goal. So just to put a context around sort of like the challenges that arise in this kind of settings, let me talk about one of those applications that are implicitly multi-agent. And in particular, talk about deep generative models, which are whose goal is the following. Their goal is to come up with a neural network with well-tuned parameters X, such that when you plug into this neural network a boring sample, so a sample from, say, a high-dimensional Gaussian, what you see in the output is an interesting sample. In this case, a sample from the distribution of celebrities. Okay, so what you're thinking is that there is a distribution over faces that could be celebrities sitting in Platonic space. And what you see in the real world is samples from that Platonic distribution. What you want to do is you want to train a neural network that generates samples of faces that could be celebrities, such as the faces that you see here, which are not real people, but which are hallucinated by some neural network. Okay? This is the goal of deep generative models. And again, so this is the goal in deep generative models. And here's how a game theoretic formulation helps you attain this learning goal. In what are called generative adversarial networks, first proposed by Goodfellow, the way you get your hands at a neural network that does this job that I described is you set up a two-player zero-sum game between a player controlling the parameters of this generator network that you want to arrive at, and another player who's controlling parameters of a different neural network called the discriminator network. You set up the payoff functions of these two agents in this game so that at equilibrium of this game, the generator is generating good images. So, so the generator's goal is to take boring samples and create interesting samples. The discriminator's goal is to take samples that are either fake or real from the real celebrity distribution and distinguish which are fake and which are real. Okay, so you set up this game and you train these two agents to equilibrium at the hopes that in the equilibrium the generator is fooling the discriminator and also generating good images. There are many proposals for how to set up loss functions for these two agents in this game. So here's one proposal which leads to what are called Wasserstein GANs, proposed by Arjowski et al. So in Wasserstein GANs, you reward the discriminator to output high numbers for real images and low numbers for fake images, and give the opposite loss to the The opposite, yeah, so like I wrote it in terms of losses, you can write it in terms of utilities, but basically here, the loss of the generator is the difference between the expected output of the discriminator on a real input versus the expected output of the discriminator on an output generated by the generator. And you know, the minus of that is the loss for the discriminator. Now, what you hope is that at the equilibrium of this game, the generator is completely fooling the discriminator, and this difference is 0. I mean, this game trivially has, because you know the discriminator can always take a minus sign. You know, trivially the discriminator is in better place, and what you hope is that the generator can get the loss down to 0. Now, okay, so this is all just background. So the starting point, though, for this talk is that, you know, as you can see, the loss functions involved in this game are non-convex because they involve neural networks that are composed with each other and so on and so forth. And they're also high dimensional because these neural networks have millions or billions of parameters. And these games have no equilibria. Okay, so for a game to have equilibria, you need that the loss function is convex in a player's own actions. And here you have a game where this is not the case. And without equilibria, what is even the optimization target in this case? So this is the motivating question for this talk. So without much clarity about this, in practice, people still trying to train GANs. And the way they do it is with a method that they know how to run. I mean, the method that works in single agent learning, which is gradient descent. So they have both the agents run gradient descent with respect to their own variables on their own loss function. So you have the generator run gradient descent on his loss function. You have the discriminator run gradient descent on her loss function at the same time. And you hope that something good is going to come out of this process. Now, the empirical finding is that this doesn't work, at least definitely does not work out of the box in the same way that gradient descent works out of the box in single agent learning. So in multi-agent learning, the picture is very complex. So gradient descent against gradient descent is unstable. And it requires a lot of effort to make it go somewhere reasonable. So let me show you two common failure modes for gradient descent against gradient descent in this setting. In the first example, the target distribution, I don't know if you can see this, but the target distribution is handwritten digits. And what you see here is what happens if I run gradient descent against gradient descent and stop the training at some number of steps. And look at what the generator is outputting if I stop the training at that step. So as you can see, so the generator, if I stop it after 10K steps, collapses to a single mode that is generating a weird symbol. Then after a while, goes to a different symbol, and then eventually settles to a single mode on yet another garbage symbol. Okay, so you have mode collapse, and you collapse to a mode that is not even in the support of your distribution. In the other example, which is where the target distribution is a mixture of Gaussians, you see another common pattern, which is that there is cycling. So here, if you stop the training at different steps, the generator is picking different modes of this underlying mixture distribution and generating on that mode until the discriminator catches up with them, and so on and so forth. So they're chasing each other. So, and that's very common. Okay, so I predict, I mean, it's clear from these emerging applications that we are going towards a world where there's going to be multiple agents all endowed with complex models involving neural networks that are going to interact with the world, collecting samples, making decisions, and changing the state of the world. And in that future or present, we know that gradient descent against gradient descent is not the algorithm that is going to lead to good models, because it has these issues that I was talking about before. It is unstable. So this raises the question, okay, so like, how should we extend this paradigm that worked well for us in the single agent setting to the multi-agent world? Or more concretely, are there meaningful optimization targets in this setting? And are they practically attainable via some nice method like gradient descent? So these are the questions that I want to ask. Okay, so let's put some notation around the question. So the types of applications that I'm thinking about are those involving a bunch of agents. Every agent is making a high dimensional decision, and every agent is interested in a loss function that depends on their own decision and the decisions made by the other people. And so what makes it a non-standard game is that these loss functions that each of them wants to minimize are not convex in their own choices. Okay, and more specifically, the types of sets I'm interested in are those where, again, each of them makes a high-dimensional decision. Maybe the actions, the strategies are a couple, like they must satisfy some couple constraints. Maybe like one agent is imposing constraints on the other agent. Like if somebody produces, 10 kilos of, bananas, the other person can buy at most 10 kilos of bananas. So there are some constraints S on the strategies. And again, so what makes it a sort of like a deep learning setting is that these loss functions are non-convex. Agents have access to them through, cheap access to them, like first order access, so zero order access or first order access, and higher order access gets more expensive because we're in high dimensional settings. But at least I want to assume that these functions are differentiable and smooth at least almost everywhere. So these are the types of games that I think will comprise are already of interest, but will become even more in the future of interest. And I call those smooth non-convex games. Okay. Now the right term is smooth non-concave games, because in game theory we're talking about utilities. The utilities should be concave, and in these settings utilities are non-concave. So the right term for game theorists would be non-concave games, but the right term for machine learners is non-convex, because we're talking about losses. Of course, losses and utilities are minuses of each other. So for us, let's call them non-convex games. And as I was saying earlier, non-convex games are bad because they trivially do not have equilibria. Here's an example of a zero-sum two-player game that is non-convex and has no equilibria. You have two players, each of them chooses, is supposed to choose a scalar. Now, the loss of player one is the difference squared of these two choices. The loss of the other player is minus that. Now, this game obviously doesn't have equilibria because, if at a pair of points x1 is not equal to x2, then x1 is going to go and land on on player two strategy. But if x1 and x2 are equal, then x2 is going to get the hell out of there. Okay, so go as far away as possible. So this game has no Nash equilibria, and because it has no Nash equilibria, because this general class of games I'm interested in has no Nash equilibria, the question is, what is the right optimization target? If I were to extend, deep learning to this world, what should what is the normative? What is the recommendation about what is a good optimization target in this case? And is it attainable? Okay, if I identify it. All right. So what I mean by meaningful here? At the very least, it has to be universal. It should always exist. If it's an optimization target, it should at least exist, right? And it also should be verifiable with information that players have. If the agents have only, first order access to their utilities, being at equilibrium should be verifiable with that information that they have. If they have, higher order information, maybe it should be verifiable with the information that agents have. Practically attainable, it should be reachable through gradient descent or some similar lightweight method. Right? So that I can write my, TensorFlow, multi-agent TensorFlow package and, ask people to express their problem in my package and, give them a bunch of optimization methods to, optimize it. All right. So, all right. So what is the reasonable optimization target? Well, I don't know. But here's a very weak optimization target that you might be interested in, which is called local Nash equilibrium. What is a local Nash equilibrium? Well, it says that it's a point, it's a collection of strategies satisfying the constraints, such that for every player I, xi star, what they are playing, is at least a local minimum of their own loss function. If you keep the other people's strategies at the star values, and you were to allow this agent to locally optimize his utility function around xi star. It's a really weak solution concept. At the very minimum, if you're training a bunch of robots doing things, there shouldn't be a robot that can tweak their actions around what they're currently doing to improve their loss function. It's a very weak solution concept. It's not like necessarily like that strong, but at the very least you would like to satisfy this. And like the weakest variant of that is when this local min is a first order local min. So first order local Nash is a point where everybody plays a first order best response to their opponent's strategies. All right, so, okay, look, what does this mean mathematically? Okay, so xi star is a best response, a first order best response to x minus I star means that it's a best response as far as the first order Taylor expansion of their loss function around x star is concerned. Okay, so what does that mean? If this blob are the constraints imposed by the actions of the other players on player I, so this is this blob, player I must find himself in one of these two possible states. Either what they're playing now is on the boundary of the constraint set, and if they were to do a gradient descent step, that would take them outside of the constraint set. And if they were to project back down into the constraint set, they would land at the same point. This is like they're pushing against the boundary, and a first order step wouldn't, after they project back to the constraints, gets them back where they are. The other possibility is that they're playing inside the constraint set, but the gradient is 0. So first order steps don't go anywhere. Or, in math, compactly, this is what it means, right? So it says, if I were to take a gradient descent step on their loss function with respect to their own variables, fixing the other guys, and project back into the constraint set, they land back where they currently are. So they're like, okay, as far as my first Taylor expansion of my loss function is concerned, I can't do anything. Okay, I'm kind of pleased. Yeah. So this is first order local Nash. Right? Again, it's a very weak solution concept, but at the bare minimum, I wouldn't like to be a robot that has a first order improvement available, right? So like, it's a weak solution concept, but it's a, at the very least, I would like to satisfy that at an optimization target for multi-agent deep learning. Now, the good news is that if the constraint set is convex and compact, this thing is guaranteed to exist. I mean, All right, I mean, this is kind of like a fixed point equation, right? I mean, this is no surprise. It really follows from Brauer's fixed point that this thing exists. So that's cool. It exists, and it's also verifiable with first order information. So agents don't need, Hessians, etc., to verify that they are at the first order local Nash if they are at the first order local Nash. Little asterisk, you might want to strengthen this definition and say, okay, like how about second order Nash, right? I mean, not only do I want to not have a gradient descent step, but also I want my Hessian there to be, locally positive, positive definite or something. You can extend this first order local Nash to a second order local Nash in this way. Unfortunately, you lose existence. So, you cannot, propose that as an optimization target always exists. It may not exist actually. So that's the bad news, but the good news is that the first order one does exist, okay? The question is it practically attainable? Okay, so it does exist, so reasonable target. Is it practically attainable? Well, this picture suggests not, right? Because I mean, the fixed points of these dynamics that practitioners are running in this kind of settings are exactly this first order local Nash solution, right? I mean, the fixed points of these iterations are only going to settle at the fixed point for the gradient descent map, which is exactly this first order local Nash equilibrium that I'm talking about. And in practice, people have a hard time getting this to converge. Is there some inherent reason for that this happens? So one recent result that we proved is that there is indeed an inherent reason. And the claim is this, that even in two-player zero-sum non-convex games, any method that accesses losses via first order information will have to make exponentially many queries in the dimension and or the approximation that you're shooting for to compute even an epsilon approximate first order local Nash equilibrium, namely a point where this fixed point map that I was talking about, only makes an epsilon movement. But I mean, if n equals 1, if you only have a single agent, this solution concept is very tractable using gradient descent. You can compute such things in poly 1 over epsilon time and queries to the functions. So first order methods, if n equals 1, if you only have a single agent, this is computable. If you have two agents, even if the setting is zero sum, it's not computable. If it's a two-player zero-sum game with convex functions, it's also computable because of von Neumann's minimax theorem and its connection to convex programming. All right, but if you drop, okay, n equals 1 is tractable. N equals 2 zero-sum with convex function is tractable. But if you mix the two, n equals 2 n non-convex functions, even if it's zero-sum, it's not tractable. In this sense, that you need exponentially many queries to get an approximate first order local Nash equilibrium. Now, okay, maybe you have richer access to the utilities, maybe second order, third order, whatever. That's not going to help you. So a conditional result subject to the complex theoretic assumption that p-pad is different than p says that any method will have to take super polynomial time in the dimension and or the approximation to compute such a thing. Again, this is the previous one was just a query complexity lower bound. This one is a conditional result subject to p different than p-pad. So in summary, the result, as you hopefully in this audience know, p-pad is the class of problems that contains P and is contained in NP and contains things like computing Brauer fixed points and computing Nash equilibria in convex in normal form games, the standard game studied in game theory. So what we show is that, like in the non-convex world, even two-player zero-sum games are intractable, at least as hard as any problem in PPAD, and equivalent to these problems. But now I have 2 minutes, and I wanted to give an intuition for the proof. That's going to be a quick one. So why is it that, again, single agent non-convex minimization is tractable, but the moment you introduce another player in the picture, it becomes intractable? Why is that the case? Well, to see some intuition about that, consider objective improvement steps in a single agent minimization problem. So here I have an agent who's trying to minimize an objective, and controls move in both the horizontal and the vertical axis. And they're doing improvement steps of the objective. Well, at every improvement step of the objective has to go down, which means that as you're moving along a better response path, you make progress towards a local minimum. And also, if your objective is bounded from below, and if you're more greedy and you only make epsilon improving steps, then you're chipping away progress towards a local minimum as you're making those steps. And this is why gradient descent converges in poly 1 over epsilon steps, basically. This is the real reason. This is the only reason, basically. In the two-player zero-sum case, though, here's what may happen. So here I'm showing you better response dynamics in a two-player game where one player is controlling moves along the horizontal axis and one is controlling moves along the vertical axis. And I'm showing you the objective value of the horizontal player. Well, along horizontal moves, the objective has to go down. Along vertical moves, the objective has to go up, because when a vertical player moves, they want to maximize the function. It's a zero-sum game. Importantly, though, in a two-player zero-sum game, two complications arise. So one is better response dynamics might be cyclic, something that you cannot have in single agent optimization, right? Like, single agent optimization, the objective has to go down, so you cannot get cycles. But here you can have cycles because you can recycle 3 values and get cycles. So they're cyclic. And also, even if they're not, if you query some better response dynamic that is non-cyclic, that is a path, you get no information about how far you are from the end of this path, because you're really recycling 3 values. You get no information about where the end of the path is, even if it is a path. Of course, if it's a cycle, you don't have an endpoint. Okay, so to turn this into interactability proof, we would like to hide the long such path that is, space filling and, where you query it everywhere and you get no information about where the local min maxes are. We were not able to do that unless, what we did is, to implement that intuition, we had to first show the complexity result to show that the problem is PPD complete and exploit some structure of the proof to turn some lower bounds for fixed point problems to lower bounds for this problem. So we didn't know how to do it directly, but we were able to do it as a corollary of our complex theoretic assumption. And a big chunk of the issues were to have a construction that gives rise to a smooth function. Like if you do this construction, this PPD completeness proof, you get discrete objects. And to turn this discretely defined function on a grid into a smooth function for the lower bounds we're trying to prove, it wasn't that easy high dimension, so we had to do a lot of work there. Long story short, the philosophical corollary I want to draw from this result is that multi-agent deep learning cannot be based on the same paradigm that a single agent deep learning was based on. and that we need to do a lot more work interacting with domain experts in the applications that we're interested in, to define to model the setting, choose the right learning model, and decide what are meaningful solution concepts. And then also develop algorithms that target them, which is really what took place in this, recent breakthroughs in AlphaGo and poker. These are not just deep learning, okay? In fact, poker uses no deep learning at all. All right, so this is my biased opinion of what are opportunities to pursue. I'm not going to get into those for the interest of time. There's a lot of brewing work in this space. But the point is that we're working on it. And topically, there was just a Simon's program whose main motivation was to pursue problems of this interaction between learning and games. And hopefully in the next 10 years, we can report on the progress. So thank you very much.
Thanks, Kostas. We're a little over time, so maybe we'll just take one or two quick questions. If there's anyone, please raise your hand.
So one possible intuition, while even in benign things, like the two-player game could be very, very different than the one-player, is the following. Like intuitively, if you just have one player, you could think that every move improves your skill level. But in two players games, it seems that maybe once there is a gap in skill, there is no reason for any further movement, because the weak player doesn't really have any move they will always fail. And then the strong player doesn't have any incentive to become better. Is this something you see, or is this something you can formalize?
Yeah, so that is one of the reasons, like in my slide about GANs. That's exactly right. Like, I mean, this is one of the reasons that you see, let's say, the generating player making no progress is because, like the discriminator is killing the generator. Like the discriminator is so strong that the generator has no local moves available that could do anything. And there, it's important that the skill levels of the two players, their complexities grow together. You cannot have a super powerful discriminator and a very weak generator, or the other way around. So there are some games of this form, and this goes into the bells and whistles that the community has to add into the problem to, get reasonable practical results. This, like a joint, growing the complexities of the two players. So that's one stratagem that they do in practice.
Okay. Over there, Shanghua.
Yeah, fascinating. So I'm, on one hand, I'm fascinated by the fact that when you move away from one player, suddenly this zero sum became drastically different. But I'm also quite fascinated by the fact that they still stayed in the PPAD. Somehow they didn't shoot over to PPAD.
Right.
So what happened to that direction?
You mean why they stayed in PPAD? Yeah. Because it's a fixed point problem ultimately. What was your follow-up question? So, yeah.
So ultimately the existence proof went through.
Yes, okay. The existence is because of that. Like the moment you make the constraint set non-compact, then you lost existence. Yeah, a quadratic you cannot, even with compactness, you cannot fix. Like a quadratic, even constraint equilibria don't exist. So that is not an issue of, it's really an issue that it's a non-convex game. But what I'm saying is the existence of these solutions, first order local Nashes, it comes from, the fact that it's a fixed point problem ultimately. Yeah. All right. So thanks again.